As a science teacher, I strive to create a classroom where learning comes not only from the teacher, but from the students engaging with the subject and each other. This is no easy task, but I am able to achieve this by hooking students' thinking on a subject with an anchoring phenomena, leading a group discussion on the phenomena, having the students model their preconceptions so I can adjust the lesson to suit their needs, creating labs related to the phenomena and that cut across standards and practices, and providing students with opportunities to understand their own thought processes through metacognition. Now, I'd like to go through some of the different practices that show my science teaching. I'd like to start with explaining and modeling content. So explaining and modeling content is a teaching practice that makes subjects, topics, and strategies explicit for students. So for instance, I have an example down here where I model and explain energy using the example of a roller coaster. And I probably won't play a whole lot of this, but if we go down here, you can see that at different parts, I'll go through the roller coaster and have the students kind of bring up the ideas of what the energy looks like at those different places. So in a science classroom, the content you'll be explaining and modeling is diverse. It could be anything from the process of the science itself, using SIRS, or making a claim, providing evidence, and showing your reasoning, or even just reading scientific textbooks, or creating data, or creating representations of data. So when I'm teaching science, I really like to focus on the idea of using analogies and examples, because I feel like in science, the ability to visualize what's happening is the most important part of understanding what's going on. And some things in science you can easily just take a look at and understand what's going on, but something with energy is, well, invisible. And so having analogies and models that students can go back to can really help them to understand what's going on with it. Next, I'd like to talk about appraising, choosing, and modifying tasks and texts for a specific learning goal, also known as the mouthful practice. But when you're using this practice, the idea is that you're not always going to have the ability to create all of your lesson plans. It's not going to be something you're going to be able to do. You're not going to be able to start from scratch. So you're going to be taking lesson plans from other people and modifying them to best fit your needs in your classroom. So in some cases, you're going to find lessons that almost fit perfectly, and you'll just have to change a few things. But in other cases, you're really going to have to make some changes to make them fit not only your classroom, but your teaching style in particular. So in a science classroom, what we want to do is we want to make changes that make lessons fit more toward the next generation science standards and practices. And cross-cutting concepts, of course. But the idea behind this is, and if we'll look at my example down here, the idea that we want to really get across is some of the practices and standards that NGSS has are very good at getting students involved in the science process itself. So in this case, I had a energy lab called Popper Energy, where we took a popper, or rather, the original one, they would take the popper, shoot it up into the air, measure how high it went, or get an average height, and they would use that to figure out its potential and kinetic energy at different points. Now, in the original version, all they really had to do was create a single model of the popper itself, and only had one other analysis question. So what I did is I added, on top of a few more analysis questions that I felt better suited the ideas that we're trying to get across in these classes, I also added a whiteboarding activity where they would model out the energy at different places using two different methods, a bar chart and a pie chart, and they would then compare with another group. And by doing this, I moved it a lot closer to practice number 2 in NGSS, which involves modeling and modeling content using data, and standard HSP S32 in NGSS, which is a standard that has students develop and use models to illustrate energy at macroscopic scales. And I felt that being able to whiteboard that does that job a lot better. Generally, using this standard as a science teacher, I am trying my best to have the students do more science. I think that it's very important that in a science class, students are actually doing things themselves and analyzing data and drawing conclusions from data. The other 3 questions that I added were kind of higher level understanding questions. They have to be able to understand what those charts mean. So moving on here to eliciting student thinking. So the main idea for eliciting student thinking is that at times when you're teaching, you're going to have difficulty understanding where a student is missing the information, why they're not getting a concept. So in order for us to find that as educators, we're going to need the students to display their thinking. So we use the practice of eliciting student thinking. So this one is a difficult practice, at least for me. Perhaps not for everybody. But the idea here is that you don't want to just give your students the answer. And in order to do that, you need to use non-leading questions to probe deeper into their thinking and make sure that the student is comfortable being able to share their ideas. Now, you can do this through having classroom norms or having a safe classroom environment. But in a science classroom, it's very important to be able to elicit student thinking. In science, a great way to do this is to have students model their thinking using models, really. Well, they can use pen and paper, or I believe in this example down here, I had the student draw out the pendulum on the whiteboard in order to show their thinking visually. This is a great way of handling it, because if you can see what the student is doing visually, you can really start to understand what they're trying to get across. Now, as a science teacher, I want to create a classroom where students can openly show their thinking to me. As I pointed out earlier, I believe this is one of the hardest practices that we had to do. Apparently, you're eventually be able to elicit the students' thinking, or rather an entire class's thinking, but I had trouble even here, which is doing it with a single student. I am going to really work on this one moving forward. Our next practice is formative assessment. So formative assessment generally here is the idea of creating an assessment in order to get students' understanding. So by creating data-rich assessments and placing it to a lesson that feels natural and being able to analyze the data to see where clarifications and improvements can be made, you can change your teaching to cover these areas where you see your students lack understanding in. So for my efforts and what I strive to do as a science teacher, I want to create assessments that allow students to show their thinking as well as give me the data that I need to improve the instruction of the class. So for my example down here, I had created a formative assessment for an AP physics class where they were doing a lesson on circular motion. So I really think it's important to have a formative assessment be short. I feel as though students, perhaps not in an AP class, but in some other classes usually, will have trouble once they start to get to the bottom of a long assessment at really displaying their thinking properly. So I think a few questions is really fine. I mean, if you need to get more across, you can do it a little longer. But the positive side about having a few questions as well is you have to be able to grade or analyze the data. And if you make it too long, you're not going to be able to do that in the time needed to go back and make more lessons in order to fix any misconceptions or problems that you might have found. So here's an example of me analyzing the data, and I don't think it has to be fancy. The idea here is you create a visual that you can look at and quickly see where student thinking is going. Now, in this case, the class actually had a very good understanding of what was going on, and I was certainly impressed with them. The vast majority of them got it right, but the few that didn't, I was able to help them later on and go back and help correct their misunderstandings. And finally, we get to our last practice on here, leading group discussion. So, students, we kind of, at this point, get back to my original point that I made when starting out here. Students in a classroom shouldn't only learn from the teacher. They should learn from engaging with the subject and with one another. And I feel that group discussion really encapsulates the idea of students learning from one another. So, in a science classroom specifically, I think that group discussion is a powerful tool. I could almost go as far as to say is that they're necessary. That's what science is. It's a collaborative effort to come up with new ideas about the world. And if you're not doing group discussions, I mean, are you really doing science? That might be going too far, but I feel like in my classrooms in the future, I am going to have group discussions at least once per unit about different scientific phenomena. And you can see down here an example of a group discussion that I had recently in my core physics class about I showed a race between a buggy cart and a fan cart, where the buggy cart, which was moving at a constant speed, pulled ahead quickly, but the fan cart, before the finish line, just barely ended up winning because it's moving at an accelerated speed. In this particular group discussion, I don't think I did the best job. I'm still working on my talk moves and working on making sure my class feels at ease. Unfortunately, in this one, I believe I only had about half the class participate. The rest was there. I was listening, but I couldn't quite get everyone working on it. Here's my general idea. It comes from my school, Oakland University, of creating an arc of questions for leading group discussion. So you'll have your initial question, but then you'll build in to another set of questions that will be about a specific topic that you want to cover, or content that you want to cover. And from there, I feel that is the best way that you can really keep your students on track while you're having these group discussions. So to reiterate what I said at the beginning, I strive to create a classroom where learning comes not only from the teacher, but also from the students engaging with the subject and each other. I hope that by seeing how I manage these different practices, I was able to put forward the idea of what I am like as a science teacher.